Yeah, the rise. It happens really quickly. Do you know exactly where it's going to happen? What is the challenge in today's lab? Okay, calculating where it happens. Any other challenges in today's lab? Okay, it's not just recording the data points. Lots of people can record the data points. Lots of people can calculate where it's supposed to happen. But lots of people also fail miserably in this experiment. Because they can't make adjustments. You have to make little adjustments as you go, because even if you calculate it, it should happen at this many milliliters. And your calculation's off, or your initial titration's off, then you need to keep an eye on the data, on the pH data. I don't know if you caught this, but I said something about looking at the pH. Catch that? Yeah. Phenolphthalein, the standard indicator. This experiment, used to have a procedure, but the procedure always had to be adjusted a little bit. And it turned out that people end up following the procedure word for word and end up collecting bad data, data they really can't use. And so we're going to forego the procedure, and we're just going to go ahead and collect the data ourselves, and you guys are going to try to figure out the procedure. Actually, this is how labs are normally done. Labs are normally done where you don't follow a preset set of instructions. You figure out what you want to do and how you're going to do it. And so what do we want to do? What is the goal of today's experiment? The goal is to get a good, high resolution data set. In other words, the goal is to collect a good set of data. And so I tried to talk about this yesterday. I'm not sure how many people understood what I was talking about, but let me see. Do you know the challenge today? The challenge is there's a trade-off, because if we had an infinite amount of time, then there would be no challenge. I just tell you to collect drop by drop, and then you can follow a set procedure. Add a drop, stir it, wait for the pH to stabilize, record the pH. Add a drop, stir it. And that's a very simple procedure. Very, very simple procedure. And that's fail-safe, because you're guaranteed to get a good set of data there. The problem is this. Can we do that? Is that a practical way of doing it? Is it a possible way of doing it? Can we do that? Yeah, we don't have enough time. If I could write a procedure, that would be it. Add a drop, stir, wait for pH to stabilize, record, repeat. Repeat all the way to 50 milliliters. Your data will come out excellent. Instead, this is for you coming in. Instead, we have to do what? What's the challenge for today's experiment? Well, to get a good set of data. How do we get a good set of data? You have to know what you're trying to collect. What are you trying to collect? Well, we're trying to collect enough data in the limited amount of time that we have, and so this is what we're going to do today. I don't want to keep repeating this, but basically we're going to run a trial titration first. Trial titration is to show us where the steep rise is, if it's monoprotic or diprotic. Trial titration is just a simple titration. You titrate it with phenolphthalein. And so what you'll do is you'll take maybe like a half a gram. You know, we don't know what the unknown is, so you know we have no idea how much to weigh out, because you know half a gram might be way too much or it might be way too little. But how do you know? And so we'll take a half a gram of unknown and dissolve it in water. Well, how much water do we dissolve it? We're going to dissolve it in about 20 mils of water to a liquid. And then we're going to titrate it with phenolphthalein, 20 to 25 mils. Here it doesn't matter, because this is not a pH titration. In pH titration, the amount of water you add makes a difference. In the trial titration like this, it doesn't matter because we are monitoring pH. And the pH of phenolphthalein, where color change is so high that we won't have any problem. And so we put that in here, and then we have our unknown aqueous, right? And then we're just going to titrate this with sodium hydroxide. The sodium hydroxide is called a standard solution. Does anybody recall what a standard solution is? No. I mean, okay. There is a standard solution in thermodynamics, but in titrations, what is a standard solution? Standard solution is part of the titration vocabulary or titration jargon. Standard solution. Everyone's done, if you took Chem 1A here, you've done this. You did part one of the titration experiment, or day one of the titration experiment in Chem 1A. It's called standardization of sodium hydroxide. You recall what the standard is in titration? The standards are very common. There's actually a place that they used to name the NIST, National Institute of Standard and Technology. I think the name has changed. You can buy standards out of a catalog. There are a whole bunch of what we call primary standards in catalogs that you can purchase. They're very expensive, unfortunately. There's one standard, the kilogram standard, is in locked up in some vault in France, I think, at the side. But what is a standard in general? Nobody remembers what the standard is? Kelly, do you remember? No? Megan? No. Standard, anyway, I'm not going to get into the whole thing. It's just a solution that has the standardization process is determine the concentration to a high degree of accuracy and precision. And so our standard is 0.1013 molar. And this would be called the standard, the sodium hydroxide standard. The standardization is a whole process that you do, and that you did in day one. Go back to Chem 1A, the titration lab, and then you can see the process of standardization there. But we're going to skip that. You know, that could be part of this experiment, but we're not going to do that. Fortunately, the stockroom did it for us, and so that saves us a lot of labor. We could have bought a standard, but they're expensive, so it's better just to do it yourself. All right, so we have this. We're going to titrate this, and so we just do our standard titration to phenolphthalein. Ideally, by Chem 1B, you should be able to get this to within a half a drop, you know, the end point to a half a drop. And so shoot for an end point to half a drop or 1 drop, you know. Really, you should be doing half a drop by now after Chem 4 and Chem 1A. And then you should get a decent amount of data, but we don't know if a half gram is enough. You know, when we weigh this, we need to weigh this to the nearest tenth of a milligram, weigh on an analytical balance. And so X, 0.x, X grams. This is 4 sig figs. We don't have that here. You have to walk across the hallway and use last semester's balance. It's 1A. But there's an outside door that goes in there, so we don't have to go through the lab. We can just go straight into the balance room across the hallway. All right, then what we're going to do is we're going to use this data. And so this is, we need to do a calculation next. And the calculation is to calculate or determine the optimum sample size. Ideally, how many mils of titrant should we use? Well, we should use the most we can use for this particular titration, because that's going to minimize the error in it. And so, if we make let's say we made a 1-drop error. A 1-drop error in 5 milliliters is, it doesn't seem that big, right? But let's say if you had a 1-drop error and it only took, say, half a milliliter to titrate this. If it only takes a half a milliliter to hit this endpoint, then man, that sample's too small for one thing. But let's just go with it. If it only takes a half a milliliter is about how many drops? Just about how many drops? Some people take me too literally. I said a milliliter is about 20 drops, and then somebody did this titration experiment counting drops and not even bothering recording the volume. I couldn't believe it. And they're saying, oh yeah, 20 drops to a milliliter. They thought that was exact. Yeah, so unfortunately, it isn't. It's just approximately. And so a drop, a 1-drop error in a half a milliliter is a 1-drop error in 10 drops. That's that's about 10% error. A 10% error is huge in titration, just enormous. And so, versus if we use 50 milliliters, then a 1-drop error in 50 milliliters is very small. And so, well, we're going to have potentially a 1-drop error. A lot of people are still shaky with titrations here. Some people even more than a drop of error in this titration. But, it could be expected up to about a 1-drop error. Well, a 1-drop error, it depends on the volume of titrant here. So we want to use more titrant. So if your titration only took like a half a drop, or let's say if your trial titration only took 5 milliliters, then we got to worry. Even in 5 milliliters, there's 100 drops, there's 1% error. 1% error is big. It's big because of what we do with this number. What we do with this number is that people screw up this trial titration, and then they go and they say, okay, now I slow down and collect data drop by drop to catch that steep rise I was talking about yesterday, right? And they calculate it and they completely miss it because they had this error here, and they completely passed by where it shot up, and they end up with data that is just garbage. They have to end up repeating the titration, which is very difficult because we don't have enough time to repeat this titration, and so they just go with it, the data that they have. And so this experiment, if you don't understand it, then make sure you understand it. And what is it? It is just an exercise in collecting data. That's all we're going to try to do is to collect decent data. And so we're going to determine the optimum sample size. Let's say that, okay, I had 0.5126 grams, and this took 12.31 milliliters. All right, when do we want to hit the equivalence point or end point? Well, our target end point is going to be this. And what is the end point again? In a titration. What's the end point of a titration?
pH 7.
No. A pH 7 is not the end point.
Oh, slightly basic.
No. Endpoint is just a generic term. It could be for any kind of titration. It could be a redox titration. It could be an acid-base titration. It's used in all titrations, endpoint. These are some common vocabulary for titration: standard, standardization, endpoint, equivalence point. The endpoint is where the indicator changes color and need not be phenolphthalein. And so the target endpoint, what we want to do is, we don't want it at 12.31. You know, we want to use more of the volume of the titrate. And so our target endpoint is, let's shoot for 30. Keep the calculation easier. Let's shoot for an endpoint of 30 milliliters. And that's going to keep it easier, the deal. And so what we're going to do is we're going to do a trial titration. So let's say this sample size required this many milliliters of titrant. Titrant is the sodium hydroxide. Then what we want is we want to use 30 milliliters of titrant. And so what size sample do we need to use? X grams. So we're just going to calculate X. We'll just set up ratios like this. And so what we need to do is we need to increase the sample size, because in my pH titration, I don't want to hit the endpoint at 12.31 milliliters. That's too soon. That's going to lead to high relative error. You know, 1 drop error in 12.3 milliliters is much more significant than a 1 drop error in 30 milliliters. And so we want bigger volume. But then you go, okay, why don't we go to 40 milliliters? Sure, 40 milliliters is good, but our titration doesn't end at the endpoint. Your trial titration ends at the endpoint. Our titration is going to continue beyond the endpoint, because once we figure out the optimum sample, then this is what we visualize is going to happen in our pH titration. In our pH titration, this is a special titration here. What we're going to do is stirring's a bit of a hassle. Normally, what do we use for titration? What piece of glassware do we use in titration? In a standard titration, we use a burette, and what else? What do you put your acid in, sample? The sodium hydroxide goes in the burette. What does the acid go in? One of these guys, which is called a Erlenmeyer. We use an Erlenmeyer because Erlenmeyers are easy to mix. You can swirl them without worrying about things splashing out, right? We're going to use an Erlenmeyer. We would never use a beaker, because if you swirl a beaker, you got to worry that you're going to splash the solution out of there, right? And so Erlenmeyer is great for mixing by hand. We are not going to mix by hand our pH titration. What we're going to do is we're going to use a magnetic stir. Magnetic stir is a motor is here with a magnet in it, and then we put a Teflon coated stir bar in here. And so this is a Teflon coated magnet. This Teflon coated magnet is expensive. It's like $10 or something. So if you dump it down the sink, you've just dumped $10 down the sink. And so don't dump the stir bar in the sink. That's happened so many times. Yeah, watch out. All right, the next thing is, this is a pH titration. The amount of water makes a difference. How much water do we need to dissolve our acid in? Well, let's say I calculate the optimum sample size. This is too little. I want more sample there. These are just pretend numbers. I'm just making them up, so don't take these too seriously. Your numbers are going to be totally different. Or they might be similar. 0.5126, 0.5126 times 30 divided by 12.31 gives me 1.2492. And so, you know, my optimum sample size over here I calculated is 1.2492 grams. And so this gives me an idea. And so I need to weigh close to that. Now, can I weigh that exactly on the balance? No, because a tenth of a milligram is like a fingerprint. You know, if you leave a fingerprint on there, or like a speck of dust, you know, a tenth of a milligram is very, very little mass. So you're going to be at the balance all day today trying to get that. And you probably won't be able to get it. And so just get it close. It doesn't have to be exact. I mean, if it's 30.1, it's fine. So just get it close to there. But remember, if it's not this, then you have to adjust your thinking appropriately when you collect your data. That is, if you're a little short, then make sure to adjust how you collect the data. Or if it's a little bigger, then make sure to adjust how you collect the data. And so what we're going to do is we're going to dissolve that sample in water. Now, how much water do you add? Well, if this is a pH titration, what we want to do is we want to start off at the lowest pH possible. It's an acid. And so how do you start off at the lowest pH possible? You make it the most concentrated that you can. Now, some of these samples are highly soluble, some of these samples aren't so soluble. And so if your sample is not so soluble, you got to watch out. Don't add too much water, because if you keep adding more and more water, then that could potentially be a problem, because your pH is going to start off too high. Remember, the more water you add, the more dilute you get it, the closer you're going to get to 7. And so what we need to do is we need to dissolve it in a minimum of water. And so dissolve in a minimum of water. Okay, if your unknown is not dissolving easily and you're worried about adding too much water, then throw it on a hot plate, warm it up, get it to dissolve that way. That should help you. Now, we want to dissolve into minimum water, so we start off at the lowest pH possible. However, we have to submerge the bulb. And so some of your samples are so soluble that they dissolve in barely any water. Just put a little bit of water, it's already dissolved. And so what you guys will have to do is you'll have to do the opposite. You'll have to add enough water so that the bulb is completely submerged. For you guys with the less soluble samples, then you won't have to worry, because you'll probably have plenty of water that the bulb will be completely submerged. And so this is why we need a beaker. We need a beaker so we can stick the pH probe in there. If we can't do that, then, and there's no way to stick the pH probe in here and allow the drops to fall from the burette. And so we'll position the burette over on the side here, and the pH probe here. Then we'll start stirring, but watch out, don't start stirring too rapidly, because if you do, you'll have splattering out of the beaker. Beakers aren't good for containing stuff. And so we'll just start to mix or stir with the beaker. And Teflon bar, pH probe. pH probe you can mount with a clamp here. That works. And then we record the initial pH. Hopefully the initial pH is low. The lower it is, the less potential error you're going to have, especially if you have a diprotic acid. And so lower is better. The higher it is, I mean, if you go crazy with the dilution, you're going to start off at close to like pure water or something, but that would be crazy dilution. And so we need to start off lower so that we don't miss any rises here. Now, what we predicted from the child titration is we predicted 30 milliliters we should have a steep rise. That's where, around 30 milliliters, and this we should go up to 50 milliliters. So here, at 30 milliliters, the phenolphthalein turned pink. So we expect this you know what pH phenolphthalein turns pink at? Phenolphthalein turns pink at pH 9. And so I know we're at pH 9 over here, so there's got to be a steep rise. And the steep rise happens at this. And so what we're doing is, this is invisible. We can't see this. And so what we're going to do is we're just going to try to figure out where everything's going to happen. All right, something interesting is going to happen in this area. At 15 milliliters, you might see another rise here. It won't be as dramatic. And so this would be a diprotic acid here. It's our diprotic acid. Here. Now, this is the trick. The trick is you have to map out this green curve with actual data points. Now, what happens is people will map this out. They'll go, okay, you know, at 30, I should see this rise here. At 15, I should see something like this. And so this is their plan. Their plan is this. They want to go quickly in these regions and then slow down at around 15 and slow down at around 30. That makes complete sense. And so what they do is we can take half milliliter or a full milliliter intervals here. And then before we get to 15, you know, well before we get to 15, then you go drop by drop. Drop by drop is pretty painful, but you got to do it because we want to map out. If we don't go drop by drop, we might miss the whole thing. And it's over before we know it. And so we go drop by drop and collect good data there. And then it's stabilized out. We can spread it out more because we aren't going to miss anything. Nothing's happening. And then before 30, we go drop by drop. Again. Actually, you know, this rise, do you know how many drops this rise happens in? This rise happens in 1 or 2 drops. And so after 2 drops, it's done. It's already happened. And so I'm totally over-exaggerating here this with the data because 2 drops and then it's over. And so if you're collecting data at half a milliliter or a full milliliter, if you're collecting your data at 20 milliliter intervals, a milliliter interval, excuse me, that would be 20 drops. You missed it. This thing happened in 2 drops. It's done. You completely missed it. And that's what happens all the time in this experiment is people completely miss this. They completely miss it because I see this all the time. This is what I see. That's what we planned. This is like the mental plan. I got this all planned out. I'm going to have lots of data here and lots of data here. And then, okay, this is why we do it at 30, because we want to collect it all the way out to 50. And so we're just going to collect it. And pretty soon it's just going to stabilize. When it stabilizes, you can up the interval. You know, rather than doing 1 milliliter, you can go like 3 or 5 milliliter intervals if nothing much is happening. And we take it all the way to 50, or however many you fill the burette to. And so what we're going to do here is we're going to go well beyond the endpoint. In our trial titrations, we don't go well beyond the endpoint. We stop at the endpoint. For pH titration, we go all the way to the end. We got to map this whole thing out so we see exactly what it looks like. But this is what happens with people. With people, what I see is this all the time. I see that they start collecting down here, and then they go back to big. And so they completely miss this first rise. They don't know where it happened exactly. Because this is all, remember this curve's not here. And so this is all you see with the data. And then they go something like this. And then boom, they miss this rise. They don't see exactly where it happened. We have to pinpoint that rise exactly where it happens, or as close as we can to where it happens. And so people end up collecting a whole bunch of data here, but nothing's happening, and then they miss where there was actually a change. Well, this is because their trial titration was way off. They're rusty with titrations, or their calculation was off. They just collected in the wrong spot. Or this happens. All of a sudden, they're thinking we're going at big intervals here, and then they miss it. And they start collecting small intervals. These people who do this, they aren't paying attention to what's happening with the pH. They aren't thinking, that the calculation could be off, or in other words, they were just trying to follow the procedure as written in the manual, which they were, except their accuracy in their trial titration was terrible, and therefore everything else was screwed up based on that, and they were following the procedure exactly as written, but they got a junk set of data. And so I decided, we don't need a procedure. What we need to do is we need to keep an eye on this and be aware, of this. So if you start to see a rise in the pH and it's off, then be very careful because your calculation could be off. Okay? And so if we have a diprotic acid, it's going to look like this. If we have a monoprotic acid, then there's just going to be one big rise. And so this would be like a monoprotic acid here. at 15 milliliters, even though we're going to collect a whole bunch of data, we don't know if we have a diprotic or monoprotic, but around 15 we're going to collect a whole bunch of data to see, is there rise there or no rise? If there's no rise, then it's a monoprotic. There's just one rise here due to the neutralization of that one hydrogen. And so the challenge is to collect a good set of data within the time that we have. And so that means you have to figure out, you need 50 milliliters worth of data, you have to figure out how much time you have remaining and then how many data points you can collect within that time. Okay? And so this is the challenge at today's lab. The challenge at today's lab is data collection. The goal, the purpose of today's lab is data collection. Okay? Data collection. And then we'll analyze the data later. Okay, so think today, just data collection. So. All right, any questions? Okay, go ahead and go to, you can work, let's see, you can work with a partner today. And so, work in groups of 2. Or you could work solo if you want. I'm not sure if we have enough. We probably have enough pH meters to work solo.